Okay, so you probably use the ChatGPT and Claude, but here's something most people never think about it. Can you actually customize models like train it on your own data and make it behave exactly the way you want? And turns out, yes. And the way is simpler than you'd expect.
Here's the thing, GPT-3 has 175 billion parameters, and if you want to fine-tune it, basically train it on your specific task, you need to update every single one of those. That means 350 gigabytes of GPU memory just to get started. And if you need 10 different versions for 10 different tasks, that's 10 full copies of the model. Nobody can do that. Before we go further, let's make sure we're on the same page about fine-tuning. You take something like GPT-3, a model that already knows a ton about language, and you train it a bit more on your specific use case. Medical Q&A, legal documents, whatever you need. The problem is the fine-tuned model is still the same enormous size, and you're doing this from scratch every single time. So here's the insight that makes LoRA possible. When you're adapting a model to a new task, you actually don't need to change everything. The meaningful changes happen in a surprisingly small part of the weight space. Think about a doctor who wants to specialize in cardiology. They're not relearning everything from medical school. They're just adding new knowledge on top of what they already have. LoRa works the same way. So, what does LoRa actually do? Instead of updating the original weights, it freezes them completely. Then it adds two tiny metrics called A and B alongside the original and only trains those. And when you combine A and B, you get an approximation of the change you would have made. Same result, but you're training up to 10,000 times fewer parameters. The actual math is simpler than it looks. The output becomes h equals w0 x plus b a x. W0 is the original frozen weight. B and A are the two small metrics that LoRa learns, and R, the rank, is just a small number, usually 4, 8, or 16, that controls how small those metrics are. That's the whole thing. Here's what makes this wild. GPT-3's weight metrics have a full rank of over 12,000. LoRa gets away with rank 1 or 2. How? Because it turns out that when you're teaching a model a new task, the important changes are happening in a very low dimensional space. You don't need to the full rank. Most of it isn't doing anything useful. Put some actual numbers on this. Full fine-tuning GPT-3 means updating 175 billion parameters. With LoRa at rank 4, that drops to 4.7 million. That's 10,000 times fewer. The checkpoint size goes from 350 gigabytes down to 35 megabytes. GPU memory during training drops from 1.2 terabytes to 350 gigabytes. These are not small differences. Here's how it actually works in practice. First, you load the pre-trained model and freeze all its weights. They're not getting touched. Then you inject tiny A and B metrics into each layer you want to adapt. You run your training data through, and only A and B get updated. Then, when you're ready to deploy, you merge BA back into the original weight. The final model is identical to a fully fine-tuned one, with zero extra latency. Inside the transformer, LoRa doesn't get applied it everywhere. The paper focused on the attention layers, specifically the query matrix WQ and the value matrix WV. The key and output matrix and the MLP layers stay frozen. WQ and WV turned out to be the sweet spot, enough coverage to get great results without blotting the number of parameters. The paper didn't just guess, they ran the experiment. WQ alone gets 70.4, WV alone gets 73. Put WQ and WV together and you jump to 74, with only 9.4 million parameters. Adding all four metrics gets you 74.2, barely better, but double the cost. WQ and WV is the answer. This is figure 3 from the paper, and it's pretty fascinating. What it's showing is the similarity between directions learned at rank 8 and rank 64. And the result is the rank 8 directions are almost entirely contained within rank 64. In other words, the important structure is already there at rank 8. Going to rank 64 isn't giving you anything meaningfully new. So what rank should you actually use? The paper tested r equal 1 all the way to r equals 64. At r equals 4, you're already at 70.2. At r equals 64, you get 70.4. That's 16 times more parameters for a 0.2 point improvement. The conclusion is pretty clear. Rank 4 is enough. Higher rank is mostly just wasted compute. So does it actually work across GPT-2 and GPT-3? LoRA either matches or beats full fine-tuning. Training on GPT-3 is 25 faster. GPU memory during training drops by 3x. And there's no extra latency at all because you've already merged the adapter back in. Same performance, a fraction of the cost. This is one of LoRa's biggest advantages over other approaches. Figure 5 shows what happens with adapter methods. In short sequence real-world scenarios, they can slow down inference by over 30%. LoRa sidesteps this completely. Because you merge BA back into W before you ever deploy, the final model looks exactly like a fully fine-tuned one. No extra layers, no overhead. You're probably already using LoRa without realizing it. Every custom model you've downloaded from Civitai, those anime realistic or character LoRas for stable diffusion, those are literally LoRa adapters. Hugging Face's Path library uses LoRa's as its default. And LoRa didn't stop at itself. The 2021 paper basically kicked off an entire line of research. LoRa in 2023 added quantization on top, so now you can fine-tune even larger models on a single consumer GPU. Then came LoRa plus Dora, Loft Q, all variations on the same core idea, each pushing the efficiency a bit further. Now, LoRa isn't a perfect solution. Rank selection is something you have to figure out through experimentation. Get it wrong and you will underperform. Serving multiple different adapters at the same time gets complicated once you've merged them back in. And for really complex tasks where the distribution shift is large, full fine-tuning might still come out ahead. Before LoRa, if you wanted to fine-tune a large model, you basically needed a data center. Now, a simple RTX 4090 can fine-tune a 7 billion parameter model, and the shift is directly responsible for the open-source LLM explosion. Here's what I think makes LoRa special. The elegance isn't just in what it does, it's in what it doesn't do. It doesn't touch the original model, it doesn't try to approximate everything. It just finds the small space where the importance changes life, and learns that. If InstructGPT taught AI to listen, LoRa gave everyone the tools to do the teaching. Things to take away. Full fine-tuning is way too expensive for most people. LoRa freezes the original model and only learns two small metrics, A and B. Rank 4 is usually enough. At deployment, you merge it all back in. Zero extra latency. And more than any other paper, LoRa is what made the open source LLM world possible. Before we wrap up, QLoRa took LoRa and pushed it even further. The idea is you quantize the base model down to 4-bit first, so it uses a quarter of the memory, then apply LoRa on top. The result, you can fine-tune a 65 billion parameter model on a single 48 GB GPU that used to require 780 GB. If you want to dig deeper, all 4 papers are linked on screen. I'd start with the LoRa paper itself. It's dense but very readable. Then move to QLoRa right after because it builds directly on this.
So that's LoRa. Freeze the original, learn the change, and merge it back. And before this paper, fine-tuning a large model was something only big companies could do. And LoRa changed that. And it opened up AI for everyone.